Hey everybody, and welcome to the next session, Supercharge Your Code for Optimal Database Performance. My name is Gerald Venzl. I'm a Distinguished Product Manager for Oracle, and I'm going to take you through today a couple of best practices and tips and tricks of how you can make your code faster or interact faster with the database so that you don't have to wait for the database or for the DBA any longer. As said, I'm currently a database product manager for Oracle, but actually before that, I have been a Java developer for a long time. I went on from Java development into performance engineering, where I specifically focused on overall systems performance tuning, and that's how I kind of got my toes into database land as well. And then followed on to be an enterprise architect, which gave me a nice opportunity to really see how end-to-end systems are built, what the obstacles are, what the pain points are. If you want to follow me on Twitter or on blog, here are my contact details. If you would like to ask questions during the session, feel free to do so, but I'll intend also to stick to the 35 minutes and the 10 minutes Q&A, so completely up to you whether you want to ask questions through the session or in the Q&A. Just because there is some slides and live code, please, if you put questions in chat, that's fine, but I will probably not going to see them until the 35 minutes are over, as I'm in slide presentation mode, etc. So yeah, one thing first, before we jump in. So these performance numbers that I'm showing you here, and performance tips and tricks that I'm showing you here, they are not a guarantee for your particular problem. Performance is always very complex. IT seems to have the slogan, it depends, right? So just because I'm showing you something here doesn't mean it will solve your problem. Please don't be one of those guys who read something on the web or see some guy talking about something and now changes the code base and everywhere applies this best practice, perhaps out of context. So while the techniques here can have a huge positive impact and are sort of best practices for a general purpose for most of the interactions with databases that you see, just stick to computer science and do your science part of it, do tests, make sure whether actually that problem you're having is solved by the particular best practice or not. And then of course also performance is relative. So the numbers that you will see here, they actually a little bit tweaked as to make them a little bit more prominent, right? So everything I show here is running on a tiny little 2 GB Docker container on my 16 gig MacBook. So that should not necessarily reflect the numbers that you would see on a server somewhere in the cloud. So, don't take the numbers one-to-one as you go on to your production environments or your test environments. As said, performance is relative. Now, with that, let me jump in and talk a little bit about the genesis of the sessions actually. So it's like why did I actually start this or thought that this session would be good, and hopefully you all also think this will be really interesting and are curious about it. It's basically coming to the fact that in 2020 and 2010s we kind of have acknowledged that Java is a high performance programming language out there. It's used in pretty much any backend around the world that we have, and it's super blazingly fast. There is no issue with the language. The same is true for C++, the good old days where we said C is much faster, C++ is much faster than Java, kind of like 30 years behind us, and even other programming languages. We in general just got to the conclusion that we say, look, programming languages are fast, right? They're just executing machine instructions on the CPU. There's no issues with them. So it doesn't really matter. Of course, one programming language maybe is slightly different characteristics than other programming languages, but in general, they're fast. And the trouble I always had is like, this was actually something that went back a while ago. There was one guy who particularly was like, oh yeah, databases are just inherently slow, right? So as soon as the database comes into the picture, it's like your application will never perform. It's just slow, it's just like you basically just have a lot of disk IO on the other side of a network, and it doesn't make any sense. And kind of like that was like, well, that's not quite true. And this kind of gave this genesis to this presentation where I will explain some of the concepts from databases that will hopefully help you understand a bit more what's happening on the other side and why things are happening the way they are happening. And of course, last but not least, to supercharge your code and make sure that your application runs really, really fast. Because as we will see, a lot of the poor database performance actually is not so much like the underlying disks or something of the database, but more like how we interact with the system. Before we go in, a quick exercise on what performance actually is. So this goes back to my performance engineering days, and this has helped me a lot in the past to figure out whether we are even on par with the performance metrics or performance criteria that we signed up for, right? So often you kind of like, you hear people that go like, oh, we need 100,000 transactions per second. And the most powerful question that you can ever ask is just a simple word, why? And a lot of times people figure out that, well, a lot of times then people don't really have a clear answer to it, or a lot of times people, as they kind of do the math to it, they figure out that like, yeah, they want to do 100,000 transactions on a tiny 8-core machine. That's just not possible by the way what we're doing. So what is performance? I came up with this, of course, I'm a very simplistic guy, so I came up with a simplistic formula to remember for myself really, really easily. And it really just comes down to this. So performance is like latency times throughput, right? That's essentially what when you're talking about an overall system and you have performance criteria of how fast something has to happen, that's really what it comes down to. Latency and throughput. Latency is the time it takes to process a unit of work, whatever that unit of work is, right? Like how long does it take to get something done, whether that's on CPU or talk over the network or what have you. Throughput is the amount of units of work that you can do in parallel, right? That you can do concurrently. And I specifically call them here units of work and not transaction, because a unit of work in itself is kind of something to to be defined as well. And then usually it's kind of related to the business object. So it's kind of like, okay, processing one like one credit card transaction or processing one checkout or what have you. And then again, very simply, a unit of work is either being processed, which means it's on CPU using up CPU cycles, or it has to wait, which is what we would usually call I/O, input output. Now, a lot of people confuse it sometimes with just this, but it could be network, could be the user, and so forth. And the goals really are to process the unit of work as efficiently as possible, so kind of get the latency down as low as possible. For that, you may want to reduce wait times as much as possible as well, and also avoid unnecessary resource consumption so that you can process more units of work in parallel on the system, something that is very often overlooked or we don't care enough about. But if we don't eat up all the CPU but only 50% CPU, well, there's another 50% CPU available for something else not to run. Same if we don't eat up the connection and so forth, somebody else can use the connection. So quick example, right? So it's like, let's say we have like these, okay, we need to process 10,000 work units per second. What would this formula equate to? So it's like work units being your whatever business transaction, whatever it is, you want to do 10,000 per second. Well, it could be something like this, right? If you have a latency of 1 millisecond for such a work unit, that means you can do 1,000 per second. That means you only have to do 10 work units in parallel and you get to 10,000. Very simple, right? And that's actually really, really interesting and really powerful to just kind of apply this little formula, because like, let's say, okay, what happens if the latency is actually 10 milliseconds, right? We just have to process and the processing just takes 10 milliseconds until we get faster CPUs or what have you. What does that mean actually? Well, that means we actually need to process 100 work units in parallel to reach the same 10,000 work units per second. Sounds very simple, but kind of the lesson learned here that I had, that I learned years and years ago is like, well, if you cannot process those 100 work units in parallel, and if you cannot get this latency down than less than 10 milliseconds, then we don't even have to ever consider that we can process, for example, 100,000 work units per second. Just simple math doesn't really, it will just not work. We have to figure something out at that point, whether that's reducing the latency, scale in terms of concurrency of parallelism of throughput, or perhaps split the application or the system out altogether and divide and conquer, basically. So something that hopefully helps you a little bit in your days when you think about performance, very quickly, something to do very quickly to kind of see whether it's even feasible that you can achieve those performance numbers that you are looking at. Now, interestingly enough, when we come back to databases, one of the things, when we talk about throughput and we talk about parallelism, we kind of like our thread pools, we're in this day and age now where we have many, many CPUs or CPU threads on the application server, and we like to kind of just parallelize our work units into a thread pool or something like that, or even serverless functions, and spin up many of these, and each does a little piece. It's great. But actually, if these threads then tend to talk to a database, most of the times you will actually notice that they will get worse performance on the database side than if you actually were to just keep your interaction to a few. For the one hand, of course, every time you talk to a database, you have a network round trip, something not to be underestimated. So if you do 10,000 network round trips rather than 100 network round trips, that just adds up. Of course, they happen in parallel, but still network round trip has to happen. It has a latency associated, and there's only so much you can push through the pipe, which brings you back to the work, the throughput as well, right? And so sometimes when it comes to databases, less is more. And this is something I will demonstrate to you. I talk a little bit about Oracle database quickly, not only because Oracle pays my salary, of course, to be here today, which I'm very grateful for them, but also to just make you aware of some of the things that Oracle database has, and also other databases started to kind of introduce. Oracle has this since a long, long time. So if you happen to have an Oracle database that you're working with, you should go to your DBA, so your system, and take advantage of this. And that said, if you're not working on an Oracle database, you may find that other databases have very similar concepts that help you when it comes to performance. So, another thing that we very often as developers see or do is that we kind of treat our database a black box, right? We go like, yeah, there's a JDBC connection, and now we do something, and now stuff is happening, right? And it's like, and if it's not happening, the database is slow or whatever, right? And we kind of really don't know what's going on. But even there, we can apply some very simple thought processes or just rules to figure out what's going on the other side, so that it's not a black box, right? So it's like just like our application is either on CPU or waiting for something. The same thing is true for the database. That's actually, you wouldn't believe how powerful it is to just run a top on your app server and on your database server. And if you see that both are basically doing nothing, that kind of tells you already that something is going on somewhere in the middle. So, just like for our application, our database is the same thing. It's either working, that means, you fired off a SQL statement, whether that's an insert into statement, whether it's a select statement, and it's processing this. Or, of course, it's waiting for the user, right? It's like databases just don't spin up CPU cycles for no good reason either. Most of the times, they're actually waiting for work to arrive. And as I said, one of those things that you can very quickly figure out is when if you run a top on your database and on your application side, and you see that they are both idle, no CPU usage, no I/O going on, that already gives you a hint that something else is going on there, that it's not necessarily that you're waiting for disk, or it's not necessarily that you're waiting for network or something like that, or that you're out of CPU time. The nice thing about, when we go a little bit deeper, so a database is working, right, on your SQL statement. So again, apply the same rules. Well, it's either busy, which means like it's processing on the CPU or many CPUs, right? The database is actually doing work for you, or itself is waiting. Very similar concept that we just had from the application applies to database as well, right? And when it's waiting, this is actually when we start talking about, could be the disks, it could be the network, it could be waiting for more data to come from the application, for example. It could also be the user itself or the application itself, where databases are transactional systems. So you can lock yourself, or you can lock somebody else by running a transaction which is not completed yet, and the other user is waiting for that transaction to complete before they can complete their transaction. So that's usually what we're calling like waiting for the application or waiting for the user. And when we take this back to Oracle, in Oracle, we can actually track both of these very, very simplistic and very, very easily. It tells you pretty exactly what's going on. So the working state when the database is on CPU, we track it in something we call statistics. And when we're waiting for something else, we track these in wait events that are grouped into wait classes. And they are actually retrievable via SQL themselves, which I show here. So We have in the latest version of Oracle database 2010 different statistics of what we are doing when we are on CPU. Those are 2010 pointers of like what the database is currently executing on CPU instructions. That's actually usually much more than what any application you would ever see is doing, because we are not so good in instructing our applications. But yeah, database tracks up to 2,000 of those, you know, from like, okay, parsing your query to maintaining the index blocks, etc. And you can retrieve them very simply via this this view here, v$mystat. So that kind of shows you the statistics for your current connection, that is, right? So each connection has its own view of that, and it's just increments as they go up. So you kind of just you issue the query, and then you issue the query again, and then you take the delta of those two, and you see exactly what your session, what your connection has been doing between those two times you ran that query. That's pretty cool, gives you a good idea what's going on CPU. Usually on CPU, we don't care so much though. What's more interesting are the weight classes when the database isn't actively doing stuff. And there is, I think, up to 13, that is 13 different weight classes. And as I said, each of those have weight events coming as well that tell you what the database is waiting on. And you know, you will see some of those interesting, or ones that you will see more often. Is, you know, it's like the infamous "I'm waiting for disk" is what we call user I/O. So we're kind of putting data to disk, etc. Network, if we are actually waiting from the application to retrieve more data, for example, don't get data fast enough. You will also see concurrency, which is like when you have those 10,000 threads coming in and actually executing 10,000 into statements on the same table and so forth. That concurrency still has to be managed in a transaction system. They have to essentially use latches and mutexes to figure out who is going next. So we track this here as concurrency. And then we also have commit, which is one thing that will go in a little bit more deeper. And you see here application also on the second one. This is said as like a simplistic put. I'll do an update on the table and I go into the weekend, I don't commit, and your application is now stuck by updating one of these rows that is locked in my transaction because I didn't commit. So this is usually what you will find there. And then there's a couple of other ones. The really nice one that we also have that I'm very proud of, because those are the quick fixes, is this configuration one, because those are basically wait events you're waiting because your configuration is not great. It's like, you know, increase the table space, give us more memory or whatever. Those are really easy fixes. And as said, if you look, you know, if you just actually Google, you know, for Oracle weight classes or statistics, you may be able to actually find something for your database as well that does something similar. They are emerging now. Now Oracle does this since 20 years, so it's quite sophisticated by now. And also, you know, weight events, we have 1,920 different weight events that we track of what you are actually waiting on currently. And also that you can actually just query via this view v$session wait. Now, why am I saying you can just query this? Because often we are in the situation where, or maybe more in the past these days, but where we wait for the DBA to kind of like, hey, the database is slow, and you know, we kind of waste a week or whatever fighting with, you know, it's the app, no, it's the database or what have you. Or nowadays also with you know, cloud environments, you may just get your own database and you don't have a DBA. And so I'll point this out that all you kind of need is if you get access to this session wait on v$mystats, then you can kind of do a lot of this by yourself already. You can just query this and figure out what's going on, and you don't have to wait for somebody else and figure this out. Also, so you know, the database is talking about sessions. That translates to connections in JDBC. So each connection that you have to the database is a session on the database. We also do this for a broader scope as well. So you can, you know, you will see here you have like v$system events, which means like the entire database, right? If you're not looking for a connection, but an overall application, especially because you probably do have a connection pool somewhere and more connections are doing stuff concurrently. There's also equivalent views for the events as well as statistics for that as well. Now, let's jump into a couple of examples and best practices. And the first I would like to start is commit. a savior of your data, because it's highly misunderstood usually what a commit does. And it kind of can hurt your performance quite a bit if you abuse it. Now, of course, we all know, well, transactional systems, right? So it's like we execute some DMLs, so insert, update, delete, merge statements, and then, you know, it starts a transaction and we commit the transaction, and, you know, what's the big deal? It's like we commit the transaction. So we often see situations where you know, you would do a commit after each insert because, you know, you have a batch load or something going on. And it's like, yeah, we commit after each insert, etc. Because, you know, it's like we want to make sure that the row is in the database. But actually, you know, the thing is, you know, it's like databases are not kind of writing every insert into statement to disk, and they never really have since the 70s, since they got invented. They always had like a cache, a memory cache, in front of the disks, just like we have memory in our applications. And so when you actually do an insert into statement, that doesn't end up in disk at all. It doesn't touch the disk at all. It goes straight into memory. And that's something that in Oracle we call buffer cache. Others call it maybe row cache or block cache or something like that. But it's like your insert into statement doesn't hit the disk at all, and subsequent insert into statements don't hit your disk at all either. What does hit disk is the commit, because that's essentially when you say, okay, this transaction is now persisted, right? When the commit comes back and says, yeah, I've committed, well, then we know that the data is on disk. If we die beforehand, we know that the data is not on disk, right? We know that we have to rerun that transaction. We have to rerun those inserts into statements. So the commit is actually what will be issuing an IO. And if you do the commit for every insert into statement in, you know, 10 million rows, for example, then you will issue 10 million IOs that may actually not be necessary. The disk, where it's going at in Oracle is what we call redo logs, so that we can redo the work if there's been an outage or something. Others call it journal or transaction log, something like that, right? But that's essentially what you write when you do commit. Now, the databases are also smart enough; they don't write everything when you commit. They actually already start pre-writing to disk in parallel, asynchronous, as your insert into statements carry on. And when you actually say commit, that's when you basically make sure that everything has been written and mark these transactions as complete. But that will be the part that your connection is waiting for that to happen. While before it's just happening asynchronously as the insert intos come on, it has no impact to you whatsoever. Now, you know, when we look into the commit itself, what's actually happening, there's a couple of steps that happen. I just point this out that there's, you know, commit is like 6-letter word. It seems very simplistic, but there's a couple of things that have to happen, of course, to get this transaction completed. In our case, we generate what we call an SCN, or system change number, just an increment, that integer, like for every transaction, we just increment by 1. And then we have this background process that will write those changes. It's called the log writer, or LGWR, to the reader logs. We release logs on tables. We remove save points if you were using save points. So also some feature that's actually often overlooked in the databases, that you can actually issue save points of your transactions throughout the transaction. And then we perform this commit cleanup, as we say, basically mark this records as completed on disk, and then mark the transaction complete. And there's those 2 points that go to disk. The log writer writes to the reader logs, and the commit cleanout that may or may not happen all the time, but those are the 2 points when you hit the disk. Now, here's a simple example, right, of where you can illustrate the overhead of this, right? So it's like, I have a prepared statement. It's a very simple insert into a test table with 4 values, 2 of them being generated by the database anyway. So basically, I just pass on here an increment, an integer, and some text, right? And then I send this this insert statement over to the database, and I commit inside the loop, right? And I do this 10,000 times, and then I'll just change this and commit outside, right? So this is kind of the only line that changed, a very simple, simplistic change, and we will see the difference. So let's jump over here into my IntelliJ, and as said, here's the commit example. So this is exactly, so what we're doing here is exactly what you have seen, right? So it's like we have the insert into statement here. We take the time before the loop, we execute those 10,000, and we take the time after the loop has happened, and then we run the same thing again, where we have the commit outside here, take the time again. I also have this little guy here. It's a little monitoring tool that a friend of mine has written. It kind of shows us what's going on the database side. So it kind of pops up a graph, and we see here these wait events and CPUs. So right now, nothing's going on. So let's jump right in. I already gave some of my numbers away down there. Hopefully you guys haven't seen it. So we start with 10,000 rows. You see down here. I'll bring this up and zoom in here just a little bit for the benefit of the reader, of the viewer. So you see here, so we're running with 10,000 rows, and you can see there's like, we're actually only spending about 50% time on CPU and about 40–50% time on this event called log file sync, which is exactly the event that we're tracking for writing that data to this redo log that we have set before. So that's exactly when we say, okay, we have to write this change now to the log file. And 10,000 rows, you basically have half-half, right? What's happening there? And let's see, my system should be warmed up. I hope. I said runs all in a Docker container. That took about 40 seconds, sorry, to do so. That's actually a little bit longer than I did before. Let me just kick it off once more. But we wait 10 seconds. I'll do the other loop right with the commit at the end of the 10,000 rows, and you see we are nicely here on 100% CPU. No wait event basically, right? It's all just nicely green. And we're done here in 12 seconds. So let me just kick it off one more time, because unless my Docker container, whoops, acted up, this should go a little bit faster than that. So again, we kicked it off 10,000 rows. And so like very simplistic, by the way, this tool is querying exactly those two statements that I've just shown you before, right? So it's like, that's how, and then it just plots it into those graphs, right? So it's like, you see very quickly, there's like, okay, while we're executing this, half of the time what I'm actually doing is just waiting for this log file sync, meaning for the disk to happen. And it's kind of like, yeah, it's in my case, actually a useless wait, because I could happily just put these 10,000 rows into the memory basically first, and then just commit once. And you see that even when the commit happens afterwards, you don't even see the wait event coming up, because it's all done in bulk. Now, of course, one thing I just realized, I do have Zoom and screen sharing on, so that of course has some implications to the CPU. I anticipated that yesterday, so that's probably why this is now slower than it was before when I ran this without Zoom being on. But you see the huge difference, right? 10x difference. Here we had nice green just using CPU. So that could be the impact just by having just by committing every row that you may not need, right? So yesterday evening, this looked more like this, about 20 seconds and 7 seconds, but it kind of still paints the same picture, right? We're kind of like wasting a lot of time to just write every tiny change to disk to issue, or tell the database to issue a lot of IOs on our behalf that we don't necessarily need. Now, one of the natural questions that then always comes up is kind of like, okay, so when should we commit, right? It's like, does that mean we should just never commit? And hooray, right? We never hit this. Now, of course, we have to commit eventually. It's a transactional system, right? But it's like the point of when you commit, you can decide. And so usually what happens in the world out there, if you have a non-restartable work unit, that's usually where you have to commit every row. So very, very good example is like an ATM, a money withdrawal from the machine, right? It's like, you really don't want the customer to go there, put in his debit card and type in PIN, get some money out, and then hopefully 9,999 other people will also show up to also withdraw money before he or she gets the money out, right? So it's like, those are things that you tend to commit right away. They also are what I call a non-restartable workload. So it's not like that if you kind of miss that transaction, you're not going to call up the user and say, hey, by the way, it's like, because we didn't commit when you did this or whatever, could you go back and do it again because it doesn't reflect on your bank account? Obviously, that's not what's going to happen, right? So all kinds of these workloads where it's kind of real time, you get an order and you get a message and you have to do something. That's usually where you have no choice but to commit every row. And that's usually then when you start looking into, with the DBA guys or other folks, to like, okay, how can we make this latency for this log file sync, this IO, as fast as possible? We would usually then start looking into SSDs for these log files or something like that, and try to cut down the latency as we talked about before. However, for restartable workloads, you usually don't have to commit every row. And, you know, like one very simple example are batch loads, right? If you get a file in or something like that, or you get even, you know, messages from a queue in, nothing stops you from actually dequeuing 100 messages, process them all, commit at once, and then tell the queue that you have dequeued all of them, right? It's like if anything fails in between, those 100 messages will still sit on the queue, or if it's a file, now that's if it's a transactional queue, I should say, or if it's a batch file, a simple load, the file will still be there, right? And this is usually when you kind of come in and think about batch sizes. So it's like, you know, let's do 1,000 at once or something like that. And you know, and then we may even think from an application, okay, we read 1,000 at once from the file, and we take those 1,000 records and then give it to 1,000 threads. That's actually maybe not something you want to do, or perhaps you still want to do that, but you may want to think of a different kind of architectural concept in your app to then have one or few threads that actually take the role of persisting it to the database, and not take 1,000 rows and then 1,000 different into statements happening. Now, also don't forget a commit means, of course, a round trip to the database, right? So it's like one thing that wasn't that obvious right now that because it's all local, is like for 10,000 rows, we actually did 20,000 network round trips, right? It's like sending over the insert into statement, coming back, sending over the commit, coming back, right? Of course, if we take the commit out, we have 10,001 network round trips only, right? 10,000 insert into statements and then one commit statement. So, you know, it's kind of, you have to figure out where you want to commit, when you want to do that, but at least you kind of know now what's happening behind the scenes. And, you know, one thing that's really annoying for JDBC specifically, in my opinion, is that the JDBC driver has auto commit set on by default. That means the driver commits on your behalf by default. And I would just recommend to turn it off. It's like your application should, or you know, maybe the ORM framework perhaps should be the one that actually decides when to commit. Now, next example, row by row or slow by slow. So kind of this goes a little bit further. A little quiz here. What would you rather do on a table with 10 million rows? Would you do, you know, select my value from my purchase, where, you know, from all purchases from the 1st of September 2016, let's get how many million rows we don't know back from the network, and then just sum it up in our application logic? Or would you rather do just a sum on the value and let the database sum it all up and then just fetch one row back? Now, hopefully we all agree that the correct answer is this, right? Because we don't know how many rows they will be coming back, how many network round trips this would be, et cetera, et cetera. This would be a really inefficient way of doing the same thing, and semantically it's correct. The value will still be the same after this while loop, but we could just have the database do this. And this is something that we call set-based processing, right? So it's like we take a set of data and have the database actually do the work for us. Now, what a lot of people, you know, kind of argue about is like, well, where should the processing happen, right? Should it be on the database tier? Should it be on the application tier? I can tell you that databases work best for set-based processing. That's what they have been designed for. That's just a relational model. The mathematical model behind it's all about set-based operations. And that's where, you know, if you can basically get it into a SQL statement and a simple SQL statement, that's usually the fastest execution what you can get on the database. As to where you should process what, I'm actually a big favor of like wherever it makes most sense, right? It's like, don't have this religious argument of like, no, let's put everything in the up tier, and that means also the sum goes into the up tier, or let's put everything in the database. That kind of is more like the approach of the 90s. Do it where it makes most sense, right? If you have very CPU intensive tasks, you probably want to keep it on the up tier. If you have very data intensive tasks, IO intensive tasks for that, you know, maybe it's just best to have a store procedure, a function on the database that you call. You know, it's really not that more painful to create such a function. And it avoids network round trips. It avoids unnecessarily shoveling data around the network, which is essentially where you would wait most of the times. Now, what also a lot of people don't know is like the set-based processing you can also apply to DML operations. So we have here the same insert into statement that we had before. And here we have the same, all the same code that we had before. We do 10,000 insert into statements, and then we do one commit. You could actually rewrite this with 2 more lines by not sending 10,000 insert into statements over to the database, but actually add them up in one batch and then tell the application or tell the database, the driver, to send over that batch of 10,000 rows to the database, process it all there, and then commit. And so, you know, we do the same thing here. And that really shows you how fast databases can potentially go when you do this right, or when you can apply it, when you have your code right for the database. Again, this doesn't mean that it always works in every scenario that you have. But here again, we have this commit, and here's the interesting one, the add batch and execute batch. And let's execute this guy here. Same trick we're doing as before, 10,000 rows. So we will see the very same pattern now for the first, right? This is exactly the same code. So we're waiting about, what was it, 10 seconds on CPU time, right? And we're executing, there we go, 10.6 seconds. We sleep for 10 seconds, and then we execute this add batch functionality. And we'll see how long that will take. And ta-da, there we go, we're done. So 73 milliseconds, that is not a lie or anything. That's actually how fast a database can insert 10,000 rows if you have the right code for it. Just so that I'm not lying, I executed one more time while I explained. So basically what we're seeing here with this 10 seconds of CPU time is like still 10,000 executions of an insert into statement. The database has to do a couple of work for that, right? It kind of has to make sure the object is there, is still valid, etc. It has to execute this insert into operation. While on the second execution, what we're telling the database is like, just like with the sum before, is like, hey, here's 10,000 values. Please execute this one insert into statement with 10,000 values. So execute it only once. And there you can see actually that databases can be blazingly fast, because really what's happening is like, I basically just dump 10,000 tiny rows into memory. That's not a big deal. And then I do one commit at the end. And that's actually also not a big deal, because we're talking about a couple of kilobytes, maybe perhaps 1-2 megabytes, right? And like in today's day and age, with the hardware power that we have, it's basically nothing. So this is how fast databases can go. Of course, also with the, let me get this thing out of the way. Also with the add batch, it's like, so here's just the numbers, what I had yesterday, right? It's like a couple of milliseconds. Of course, there's no network round trip to it either on anything. But yeah, it's like a couple of milliseconds. That's not bad for 10,000 rows. Of course, with add batch, you cannot always use that either. One of the most common scenarios here, so questions asked, is what will happen if you get an error during the batch? It will abort the batch, and you kind of have like, okay, let's say the 9,000 row has failed, right? The whole batch will fail and will come back to you, and you have to figure something out. There is actually a SQL syntax that you could use that's called log errors, or the log errors clause, where the database would log those rows that failed into a separate table that looks pretty much the same as the original table, just with an error message to it and when it failed. And so you could afterwards go in and query that table and see which records failed. So that's kind of a nice trick, so that the batch will go through. You don't have to start over again. And again, it may or may not work for your particular use case, but if you can apply it, you see we kind of, in the big picture, we went for 30 seconds with commit every row, insert every row, commit every row, to 60 milliseconds. So like that's usually, when you tell your boss, okay, now get the champagne out and get me a pay rise, because that's not a fraction anymore, that's magnitude. Last that I want to cover, and I'm sorry, I'm going a little bit over here, but we're almost done, is bind variables. That is also something that's often overlooked. So what are bind variables? So parameterized statements, they also sometimes called. Well, it's basically you pass on parameters to your SQL statements. And why is that important or can be important? Well, because first and foremost, SQL statements are just strings. So if you have a string, but you pass in a number and a date and other stuff, that string will have to be essentially type converted to the database type as it comes in. And so what will happen, or that is extra work for the database to do. And also the way how databases hash SQL statements is kind of like depending on the SQL text, the string that comes in. So what will bind variables allow you to do is that you can do already the data type conversion, or perhaps no data type conversion, because you're already dealing with an integer or a data or something in your application. In your don't do any data type conversion, or do it already on the application side. Don't have the database do it. And also you may save the database a lot of time by not having to parse the SQL statement. So what does SQL statement parsing mean? So like pretty much like every database, how they work is, you have two phases of a SQL execution. You have the parsing part and the execution part. Now, of course, we're going to send in some SQL, some text strings, right? So we have to parse the text string and figure out what's going on before we carry on. Usually there's two phases to it. We call them soft parsing and hard parsing. So what will happen is when you send in the string, we do a quick syntax check. Is it valid SQL? If it is, great. Then we do a semantic check, like does the table exist? Do you have permissions on the table, etc. Great. And then we do a shared pool check, and that's basically where we say, has the SQL statement actually already been executed? If so, then just execute the SQL statement again. And that's usually really blazing fast. This is what we call a soft parse, and happens every time you basically send in a SQL statement for any kind of database to do something in that concept. And you usually don't notice it, right? It's like we did this 10,000 times before, or one time before with the 60 milliseconds. And it happens, of course, concurrently. So each session, each connection is doing it. There's a process sitting on the database side that's doing it on your behalf. So it's like not some gigantic one process that does all of that. No, it happens concurrently. You usually don't have to worry about it. So if we find the SQL statement in the shared pool or in this memory area that it is, we just go and execute it, and great. If not, this is where the more resource intensive tasks kick in. So this is where we usually go into the hard pass phase, where you kind of like, now the optimizer is kicking in. So it's a brand new statement. We have to figure out, okay, how do we access the data? Do we do a full table scan? Do we do an index scan? What indexes are on there? What ways are on there to prune the data and so forth? And then we execute we generate this execution plan, right? Basically, what you then see in your explain plan is like, oh, those are all the steps that the database does. And that is very resource intensive comparatively to the soft parts, right? So it's like you need a lot more CPUs. It involves data dictionary checks, library checks, etc. Right? We kind of like have to make sure that as we go through all these permutations of potentially getting through your data, depending on how complex your data model is, how many indexes and partitions and stuff you have on there, it's just a lot of work for the optimizer to do so. And so ideally what you want to do is kind of avoid that step as much as possible and kind of reuse the statement when you can. And the way how SQL databases do this is whenever you send in a SQL statement, you get a hash, right? So it's like the best first thing we do, we hash the string, essentially after proving some white spaces and stuff, and then generate this ID. And if we were to come in again, we check this ID. Now, if you don't use bind variables, this would happen, right? If you just send in a string where ID is 453, not only does that have to be converted to a number, but also this will generate this one SQL ID. While you send in another string with 879, this will generate a different SQL ID because the string is different. We cannot, or we do not differentiate on those values that come in because they could have different meanings, right? It could be ID equals 879, it could be a subquery, etc., etc. So we will hash that, and you will have different SQL IDs, and therefore you go for different parsing. If you were to use a bind variable, on the other hand, with the JDBC driver question mark, that SQL statement stays the same, right? And so you will benefit of this soft parsing. So you can even look this one up if you wanted to. There's a view called v$SQL where you will see exactly that, where you find the SQL IDs if you're really curious of what happens under the covers. So let's do here another last quick test, and then we round it up with here a select statement where we basically concatenate the string together and execute this and fetch it, and one where we use this bind variable. And again, we just take the time before and after, and we will see what will happen. So same code here, right? As we said, concatenation of the string. And here we use the bind variable and we set the bind variable. And hard parsing. Let's jump over here, execute that. Oops. Oops, there we go, and see what happens. So 10,000 rows, we see, first thing, 100% CPU time. Looks all good, right? That's usually where I make the joke. It's like, hey, 100% CPU means that everything's optimal, right? It's like, no, we're actually wasting tons of CPU cycles right now on this constant hard parsing of those 10,000 statements that we're sending in, right? It's like, not just because it's 100% CPU does it mean it is perfect. And then when this is finished, there we go, 30 seconds here as well. We do one more round with the 10 seconds here. And we will also see that when this pops up, it does use CPU, but it does use much less CPU, and the overall execution time is much faster. So basically, the delta of CPU, what we see here, is the hard parsing aspect from it. The optimizer working for us can generating those execution plans for a semantically identical SQL statement. So there's really kind of like the execution of how we get the data, just because the parameter changes really has no impact to it, right? And so we see here, of course, here we're slightly different. Here we're retrieving data before we loaded data. So there is more involved in getting the data back to the application, acknowledges it, you saw the results set. But you see that it's faster and it uses less CPU, right? Which allows the CPU for others to be used as well. So bind variables is something you should always use when you can. Never concatenate strings, a strong one, because they also have other bad aspects. They allow for SQL injections, right? If you concatenate strings, you could actually put in some other malicious SQL statements that will then be executed potentially, which bind variables won't do either. With that, I'm sorry, I went actually a bit more over here. We are on time now, but I'll take a couple of questions if there are any. I see there's a couple on the chat. Let me just quickly go over this and do this quickly. So what's the best practice to handle errors while using batch? I already said this before. Ideally, you use this logging mechanism. Pretty much every database has it. So then you don't have to kind of go back and restart your batch, but you would then just basically have after your batch execution, you would have a part of the code that would check the error table, whether there were any errors in there. All the statements will be in there. The DB monitor shown here, that's actually kind of like, as somebody else said. A friend of mine wrote it. It's not on GitHub out there, so it's not really widely available. It is available on his blog, but it's only for Oracle database. If you just look for DB time monitor, you will find it. It is not a small app playing back a video. I hope I showed this with a couple of times executing this over. Wonder how JDBC batches compare with set statements, as it avoids the nasty string buffer manipulation, reducing network traffic. Well, so actually what you will see, so the JDBC batch, it's of course driver specific, right? So I can only speak for the database driver, for the Oracle database driver. We accumulate all the values into one array, and we send that array over with the incident2 statement. So it's kind of one network hop that we're doing. And then, so because we were actually before also using bind variables already in our incident2 statement, there's no string concatenation or stuff going on. We just kind of basically, we have this one. We tell the database, give us a head, we'll do the SQL ID, please execute. And then we just pass on the parameters for all the executions. So there should really not be much of a difference here between the statement or the app batch and JDBC for Oracle database. For others, I'm not quite sure. What's my take on the future of XA? That's probably something we would have to take offline and debate a bit about. I know that people now kind of reintroducing them with microservices and another concept called Saga. It's kind of like write your own XA transactions sort of it. But yeah, I think we're out of time to jump onto that. I'm sorry. Good call out for Percona, gets out some good insights on Grafana. JDBC is indeed one of the greatest API in the Java ecosystem. I fully agree. Whether there will be a TCK out there, I don't know. I would have to ask our JDBC guys on that, our Java JDBC guys on that one. And yeah, so the result set concept already covers the streaming use. There is actually more coming to streaming in JDBC. I know of that. So the whole kind of streaming as well as asynchronous APIs, they're currently being looked at. And yeah, with that, I said the question on XA, or if there's any other questions, hit me up on Twitter if you like, or hit me up, find me on my blog, find me anywhere, pretty much easily Googleable, unfortunately, with my name. So just hit me up somewhere and we can continue to talk. I hope you enjoyed it. There are a couple of more useful resources here for database, for Oracle database specific. If you want to kind of, go a little bit deeper into these sort of best practices I explained. And yeah, with that, if you want to find this code, it's on my private GitHub. Now you see that I have rerun this a couple of times. There's Java 1 in the title, but if you go to my GitHub and search for Supercharge code, you can take it for your own spin and figure it out. And I apologize, I went 4 minutes over. That was not intended, but I hope you enjoyed it. And thank you very much.